Hi, and welcome to another reading of our book, Quantum Atom Optics, Theory and Applications to Quantum Technology. So we got up to section 1.3 last time, so we can continue off where we left off. So in section 1.2, what we did was to investigate how you can denote various quantum states of a multi-particle system. So we introduced creation and annihilation operators for bosons and fermions. So now what we're going to do is to build up the full kind of set of states that you can have in this multi-particle system. So the first thing that we need to introduce is the vacuum state. So we need, in order to build up the full set of states, we need basically something to apply the annihilation and creation operators to. So this is the vacuum state, and so this is more or less, you have to write this down by definition, and if you have a state containing no particles and then you apply an annihilation operator on it, then you would expect that basically you would get no state at all. So if you apply this AK to the vacuum state, then you simply get zero. But if you go in the other direction, if you apply a creation operator to the vacuum state, then you start to build up the full set of states. And so, for example, we had this operator AK, and this, if we just recap on what we learnt in the last section, so the various types of states that we have available, these are labeled by this variable K. And so our AK operator was defined as something that looks something like this. So we have a particular wave function which describes the particular quantum state. So this might be some spatial wave function of the state. And then this is the integral with respect to that particular state. So AK basically produces or annihilates a bosonic particle in one of these states labeled by K. So here we're creating one out of the vacuum. So we start with a state with no particles at all, and then we're going to create a particle with in the state K. Now, according to our definition before, what this is actually equivalent to is, again, we can write it in the position basis. So by expanding this bosonic operator in terms of the position basis, then we can write it in the equivalent way like this. And if we use the fact that this A dagger applying, or A dagger in the X basis applied to the vacuum state produces a particle at position X, then we kind of recover more or less like what we know from just regular quantum mechanics. So essentially what this is saying is that this state psi is a superposition with coefficients psi of a particle at position X. So basically, we can write down single particle states in this way. So this is how we get the equivalence to sort of your one particle Schrödinger equation. But okay, so how do we go to many particles from here? So you can probably already guess that you simply apply this A dagger many more times. So if you're talking about a two-particle system, then you apply two A daggers and so forth. Now, so let's, for example, look at the particular case when N particles occupy the ground state. So just for simplify the notation, I'm going to go from A0 just to A. And so if we had N particles all occupying the ground state, then it would be a state that looks like this. And here we need a kind of normalization factor, because actually if you multiply A dagger several times, in fact that's no longer a normalized state. And so you can see that it requires a normalization just by, say, taking the inner product of this state with itself. So of course A dagger to the n means you've got A dagger, A dagger, A dagger like this. And if we take the bra side of this will be n A's of this. And what you can work out is that actually that this thing here on 1.18 here actually eventually evaluates to factorial of n. So let me just write that here. Okay, so this actually eventually will become n factorial. So just to see how this works, so for example, if we start here, and then what you can do is you can just use the commutation relation of, say, let's say we're going to move this A all the way to this position here. So what that means is that you require this commutation relation of, so we know that A dagger A is equal to 1. So that basically means A dagger minus, sorry, A dagger minus A dagger A is equal to 1. Or in other words, A dagger is equal to 1 plus A dagger A. So if you substitute this relation into here, what you see is that every time this moves across by one spot, then you'll pick up another factor of 1, and this here is basically simply to interchange the ordering of the A and A dagger. So this basically says that whenever you swap the ordering of A and A dagger, you get an extra factor of 1. So because this has to go through n of these, then what you end up with are n terms that look exactly like this. So of course another way to write this is simply A to the power of n minus 1 and A dagger n minus 1 like this. So essentially we've gone from this expression, which is defined as well, on the how I've written it here, this expression is A to the power of n, A dagger to the power of n 0, sorry. And so this is actually equal to this, and then we can just basically recursively work out that, well, this thing here is then equal to n minus 1 of A n minus 2, n minus 2, and then you can kind of keep going so that this then becomes n minus 2, and then n minus 3, A dagger, n minus 3, like that. So if you repeat this, you can see that it's going to be n times n minus 1 times n minus 2, and so that's equal to n factorial. So the normalization factor is, in order for this thing here to be properly normalized, then you need this factor of 1 over square root of n factorial. And if you do that, then we have our proper orthogonality relations. And similar kind of arguments, what you can do is to work out that if you apply an A, like annihilation operator, on the state n, then you'll get this square root of n factor. So let's just work that out. So if we've got A applied on, so the definition of this n here, we're going to use this definition here, 1.21. So that 1.21 is 1 over square root of n, A dagger to the power of n, like so. And then what we're going to do, again, our strategy is to basically work out what this A is, well, what this expression is when you move this A all the way to the end here. And the reason why we want to move it to the end is basically because once this A is acting on the vacuum, then we can A acting on the vacuum will give 0, and so we can just forget about it. Right? Okay, so let's just work out again what happens when you move this A to the left by one unit. So we've got a dagger, and there's n of these here. So that's equal to 1 over square root of n, and we can use our relation of 1 plus a dagger a, and then this will be, there'll be n minus 1 of these ones here. And so we can continue. So basically we get two terms here. So we'll get 1 over square root of n of n factorial n to the power of minus 1 times vacuum plus 1 over square root of n factorial of a n minus 1. And then essentially you do this step again through all these other ones. And so what you'll see is that if you keep on repeating this, is that you keep on getting an extra term like this. And so the number of terms of this that you get are in fact n, because essentially every time you go through this a dagger, you'll get this factor here again. So eventually what you're going to get is n of these terms and a dagger n minus 1, 0. And then we need to properly normalize this thing. And so this is the state with n minus 1. So let's look at the, if we go back to this normalization, in order for this to have the proper normalization, let's pull out a factor. So n factorial, of course, we can rewrite the bottom in this way. And then so this is actually a properly normalized state according to this definition here. So just do a little simplification here. So this n divided by square root of n will become just square root of n, and then this will be the state n minus 1. So this basically proves this relation. And for this one, it's actually a little bit simpler even. So for example, when you apply a dagger to a dagger to the power of n like this, then so this is the definition on the left hand side, and when you apply the a dagger, so we don't have to worry anything about these things not commuting or anything like that, because a dagger, these are all a daggers, so this is simply a dagger to the power of n plus 1. And then in order for this to have the right normalization, we need to basically make this bottom n plus 1 factorial. And so we can multiply the top and the bottom by n plus 1 factorial. And this is just our definition of the n plus 1 state. So it goes like this. Yeah. So in this way we can write down what the actions of applying that annihilation or creation operator to a Fock state. And for fermions, actually, it's a lot simpler, basically because for fermions, because of the Pauli exclusion in principle, the only two states that you can have are that the fermion is either occupied or not occupied. So if you have the vacuum state, then obviously there's no fermion there, and if you apply the fermion to it, then you'll get the single particle fermion state. But then if you apply C dagger to 1, then you'll get C dagger squared, because that's the definition of 1. And we know that, from the fermionic anti-commutation relation. So we know that, so if we just go back and have a look at the anti-commutation relation. So if you have two C daggers here, and then they're the same species, so this will actually be equal to 0. And so what that means is that this is the anti-commutator, so it's like C dagger C, so that's C dagger squared, and we've got C dagger squared is equal to 0, or in other words, 2 C dagger squared is equal to 0, and so anything with a C dagger squared in it is automatically 0. So this thing is actually automatically 0. So if you create another fermion in a state, or try to create a fermion in another, where there's already a fermion, then it immediately gives 0. Okay, so these exercises here are pretty much what I already went through. So in 1.21 and 22, this is just finding the normalization factors. 1.23 and 24 are these ones, and then 1.3.3 is showing that the fermion Fock states are explicitly 0. So I think pretty much we've done actually these exercises. Okay, so that's the end of this section. So as usual, if you found this video useful, then please subscribe to our channel, and we'll be back with more readings of our book. Okay, so see you next time.